Now that we have talked about the chain rule, that leads us directly into the idea of implicit differentiation, and that's what 2.3 is about. So there are two common types of equations in rectangular coordinates, rectangular meaning xy coordinate plane. And those two types of equations are implicit or explicit equations. So implicit equations are equations where y is in terms of x. So something along the lines of y equals x squared, or y equals the absolute value of x. We're looking at a function in which the x value determines the y value. Y is a function in terms of x. So when we differentiate in this way, we're taking the derivative, or we're differentiating with the respect of one variable, x. Now, in our many years of math, we have learned about different types of equations, not just equations that are functions or that could be represented as y in terms of x, y being defined as how it responds to x. We have learned about other equations where the relationship between x and y is represented in a different way. For example, a circle, x squared plus y squared equals 1, or xy plus y to the third equals 15. These are not necessarily functions, but they are definitely equations. And the big difference is that they are not equations that are y determined by x. Yes, it is possible that you could manipulate this. You could solve this and get that y is equal to the square root of 1 minus x squared, and y is equal to the negative square root of 1 minus x squared. In theory, you could solve for y. You could split it into two different segments, two different semicircles in this case, and you could take the derivative of each of those values. But there has to be another way for us to look at this. And that's where this idea of implicit differentiation comes in. So when we're using implicit differentiation, that is a situation that is going to arise when we have multiple variables, not just y as a function of x. Multiple variables in a relationship between those variables. So how to differentiate this way? What you're really doing is you're thinking about the chain rule. You're thinking about differentiating both sides with respect to x, or to whatever variable we're talking about. Typically, you're going to be doing this in terms of x. Differentiate both sides with respect to x, then basically solve for dy dx. So you're going to make sure all the dy dx's are on the same side. You're going to potentially have to factor to solve for dy dx. So normally when we differentiate, all we have to do is manipulate or take the derivative of one side of the equation. With an implicit equation, we're going to be taking the derivative with respect to x, but then we're going to have to manipulate the equation to solve for dy dx. So the big thing I want you to keep thinking while we're doing this is the chain rule. This is just an application of the chain rule. So let's work through these examples and really tie together what this is saying. So example number 1 says, differentiate the equation, solve for y prime or dy dx. Either of those notations is fine. So here's what we're doing. We're saying we're going to take this entire equation and we're going to take the derivative with respect to x. Well, on the left-hand side, the derivative of x with respect to x is 1. X is already in terms of x. Now, on the right-hand side, think about the chain rule. Right now, I can take the derivative of the thing squared. That's going to give me 2y. But now I need to take the derivative of the inside function, which is dy dx. So the short story is, anytime you're differentiating y with respect to x, you're going to stick a dy dx on there. But the reason that happens is because since we are differentiating with respect to a different variable, we're applying the chain rule. So we understand that the way that y's function is in relation to x in this problem, even though it's not an explicit way. So when we take the derivative of y squared, we're going to take the derivative, that's going to be 2y, but then we need to multiply that by the derivative of y with respect to x, which is actually what we're solving for. So the very last step here is just to isolate dy dx. So we're going to divide both sides by 2y. So dy dx equals 1 over 2y. So keep thinking about the chain rule. That's why that dy dx is sticking around. Anytime you differentiate any part of the equation that has a y in it with respect to x, you're gonna tack a dy dx on. So number 2, we're going to take the derivative of both sides with respect to x. The derivative of x is 1. The derivative of something squared with respect to x is 2 times that something, but since then the derivative of y is dy dx. The derivative of 3 with respect to x, that's just a constant, so that's going to be 0. So we are going to subtract 1, and then we're going to divide by 2y. So dy dx equals -1 over 2y. You do not need to show a lot of steps when you're solving for the variable. You can. Okay, number 3, we're going to have a chain rule situation happening with the fact that we have x plus y squared. Even if that was x plus 3 squared, we would have a chain rule happening. So we're going to have the chain rule, and we're going to have this implicit differentiation. So go ahead and pause the video, see if you can kind of figure out how this is going to go. So we're going to take the derivative with respect to x. So thinking about the outside function, the derivative of the outside function is 2 times the quantity x plus y. The derivative of the inside function is 1. The derivative of x is 1. The derivative of y is dy dx. That whole thing is going to be equal to 2. Now we're going to isolate and solve for dy dx. So these 2's are just going to divide out on both sides. So I'm going to have 1 plus dy dx equals 1 over x plus y. So dy dx equals 1 over x plus y minus 1. Or x plus y to the negative first power minus 1. So again, keep in mind all of the rules that we've learned, product, sum, quotient, chain rule, all of those are coming together in this section. The big difference in this section is that now we're dealing with y as well. So you can see 4, 5, and 6. Go ahead and pause the video, see if you can work through these on your own, and then come back and check and see how you did. All right, number 4, we're taking the derivative with respect to x. The derivative of x is 1. The derivative of -2 times something to the third power is going to be -6 times that something to the second power. But since that something is y, I need to have dy dx here. The derivative of 3x with respect to x is 3. The derivative of 6 with respect to x is 0. Now we need to isolate dy dx. So I would be subtracting 4 and then dividing by -6y squared. So that's going to give me 2 over 3y squared. Looking at number 5, I'm going to take the derivative with respect to x. So here we have a product rule happening. So pay attention. Notice that you see that product rule. So the derivative of 2x with respect to x is 2 times y. Plus, because this is the product rule for these first 2 terms, these 2 terms right here, use blue here, plus the derivative of 2y, or the derivative of y, which is dy dx. So 2x times dy dx. All of that is that first 2xy, the derivative of that. So we're dealing with implicit differentiation and the product rule. Then we have y squared, so the derivative of something squared with respect to x is 2 times that something. Then we have our dy dx, and that's going to be equal to 0 because the derivative of 3 is 0. Now, I'm going to get rid of all these 2's. Since there's a 2 in every single part, I can just divide the entire equation by 2. And I'm going to move my 2y to the other side. So I'm going to have dy dx times something equals -2y. So I'm moving, not -2y, sorry, just -y. I'm moving my y to the other side, and then I'm factoring dy dx out of what's left, which is x plus y. Again, I skipped a lot of algebra steps here that you obviously can show if you need to. So this is going to give me final answer, dy dx equals negative y over x plus y. Number 6, we're going to take the derivative with respect to x. So the derivative of cosine of something with respect to x is negative sine of that something. And the derivative of that something is dy dx. So we're just using the chain rule here. The derivative of 1 is 0. The derivative of negative x is negative 1. The derivative of 7 is 0. So if we isolate dy dx here, we're adding 1 and dividing by negative sine. So negative 1 over sine of y. You could obviously write that as negative cosecant of y. Right now, I don't really see any benefit. It wouldn't matter however you write that. Either answer would be accurate. The first thing I'm going to do on number 7 is rewrite using rational exponents. Just makes my life easier for the power rule. Then I'm going to take the derivative with respect to x of everything here. So that's going to give me 1/2 times what's already inside to the power of negative 1/2 times the derivative of what's inside, which is 2y dy dx, equals the derivative of the other side, which is just going to be 5. My 1/2 and my 2 are going to divide out. So that's going to give me that dy dx equals 5 divided by y squared plus 2 to the negative 1/2 power. It kind of seems silly to leave to the negative 1/2 power in the denominator. Oops, I left off a y here. There should also be a y here. So that's going to give me 5 times y squared plus 2 to the negative 1/2 power all over y. You could leave your answer at that step before. I just think if the exponent is negative in the denominator, we may as well move it up to the numerator. Okay, number 8. Again, taking the derivative with respect to x. So cotangent of y, the derivative of cotangent is negative cosecant squared. The derivative of y is dy dx. That's going to equal the derivative of x is 1 minus the derivative of y is dy dx. So notice we have dy dx's on both sides. So I'm going to go ahead and move them so that they are both on the same side. So I'm going to add the one on the right to both sides. And then I'm going to factor out dy dx. So I have dy dx times 1 minus cosecant squared of y equals 1. And then I'm going to divide both sides by 1 minus cosecant squared y. So you could leave this as dy dx equals 1 over 1 minus cosecant squared y. You could also change it to dy dx equals negative tangent squared y. Either way. You could also change it to 1 over cotangent squared y. Lots of different ways to write final answers with trig properties like that. Number 9 is asking us to find the second derivative, and this is actually a little bit more complicated. So you're going to do the same process that you did to start the video or to start each of these problems. You're going to take the derivative with respect to x, so let's go ahead and do that part. And since this problem is using y double prime, I'm going to go ahead and use y prime. So if I take the derivative with respect to x, this is going to be 2x plus 2y times y prime equals 0. We're going to isolate y prime, so y prime is going to equal, subtract 2x, divide by 2y, so negative x over y. I'm going to put a little kind of like cloud around this because I'm going to need this again later in the problem. And this is the part that's different than what we have done before, and it's very different than when we just took derivatives, second derivatives, third derivatives, when we were looking at implicit equations. You're going to use this first derivative again when you find the second derivative. And here's why, and here's how, I guess. So now we're going to take the derivative of this to get our second derivative. There's going to be a quotient rule happening here. So y double prime is going to equal negative y, because the derivative of negative x is negative 1, negative y times, minus xy prime all over y squared. Let me rewrite that. And actually, this is going to become addition because it was negative x times the negative from the quotient rule. Now, we can't leave this y prime in this equation. In fact, we know the value of y prime, and what we're going to do next is we're going to substitute that value in. So negative y plus x times what we know y prime is, negative x over y. We can just use the substitution from our little cloud that I made, all over y squared. This can easily be simplified to just be negative 1 over y minus x squared over y to the third. And that's fine. Oftentimes you're going to need to express this only in terms of y, which is what I'm going to do next. I'm going to totally invade the space on problem number 10. So if I want to express this only in terms of y, there's a relationship that I learned at the beginning of the problem. X squared plus y squared equals 6. Well, that means that x squared is equal to 6 minus y squared. So I could substitute that in for my x squared. And then I could have a second derivative, which is a function only of y. So instead of x squared here, I'm going to say 6 minus y squared all over y to the third. So now my second derivative is only in terms of y, which is great. The very last problem, number 10, determine the equation of the tangent line to the graph of x squared plus 4y squared equals 25 at the point 3, 2. So the first thing we're going to do is take our derivative with respect to x. So 2x plus 8y dy dx equals 0. So I'm going to subtract 2x and I'm going to divide by 8y. So dy dx equals negative x over 4y. We are evaluating that at the point 3, 2. If we substitute in 3, 2, we're going to get negative 3 over 8 is the slope of our tangent line. And then writing this as the equation of a line, I'm going to finish this off in purple. Y minus 2 equals negative 3 over 8 times x minus 3 is the equation of our tangent line. So the big takeaways from this, implicit differentiation happens when you have multiple variables that you're taking the derivative of with respect to one of those variables. The reason that it functions the way that it is that we're just applying what we learned in 2.2, the chain rule, to a situation in which that's applying. We're taking the derivative of something with respect to x and then writing dy dx because we also need to take the derivative of that inside function. So if you need extra practice on this, look in the classroom, ask for help, let me know if you need anything, and looking forward to seeing you in class. Thanks.